All right, so what I'm doing with this is I'm not creating separate documents for filters. I keep adding to the same document. So you know, so you may see the same document listed every all of this week, but you will need to remember that I'm adding material. So you don't have, if you want to go to filters, you're looking at one document. You don't have to, you know, go and compile many documents to see what we have. Also, the book has very good notes on filters, and depending, of course, on what edition you have, and I have an old one. I have the third. The material on filters is very similar. It's on different pages, obviously, but I believe is this, well, so it's a chapter 8 in my edition. I think it's the same in other editions, and it's microwave filters. And we have started with the insertion loss method. And then from there on, we are going to be covering the material. And it's going to be very useful for your project also. So that's what also, please make sure you also read your textbook. I follow that. I follow the textbook as I present the material. So you're not going to have any conflicts between my notes and the textbook. But also please read the textbook, not just my notes. The notes are to help us talk about filters in class. Okay, last time we finished with a prototype. So we said we created this prototype, and it was n equals 2, as you can see, type of a prototype. And now we have to move the prototype into a real low-pass filter, because the prototype is nothing, all right? It's just a tool. So we take this now, and in order to make it a real low-pass filter, according to our specs and our specifications, include the value for the source impedance, which I call R sub naught, and you see here. This is the value for the source impedance. Also includes a specific value for the cutoff frequency. Okay. And the other thing that includes, which we have already taken care of, is the rejection at a specific frequency above the cutoff. And we use that rejection at that specific frequency. In last lecture, we did it extensively to identify how many sections we are going to have. Every section in the prototype, it's one element. One section can be an inductor. Usually inductors are series elements. They are always, rather, I should say, in a prototype. Capacitors are shunt elements. Now, also let me ask you, because correcting some of the exams reminded me, is there anybody who does not understand the term shunt? Shunt admittance or shunt impedance?
I think I need some more clarification on the term shunt.
Have you never seen it before? I'm not asking you as an interrogation, I'm sorry. I'm asking you to see how it was taught in previous classes you took.
I don't remember.
Don't remember utilize the term. Yeah, okay. Shunt in circuit design is utilized to mean parallel. All right. When we send a shunt inductor, a shunt capacitor, it means in parallel configuration.
Okay.
Okay. Another suggestion I have is if you if you are uncertain about the terminology, email me or the TA before you have to deal with that. If you hear me say something, stop me and ask me what I mean. This is extremely important because if you accumulate all of these uncertainties that you have, the moment you will try to solve something, they will all come up. All right. And that's going to be difficult then to start looking at that moment in time. So if I say something that you don't understand, because it is true, I have to say, and I have understood that circuits here have been taught by faculty who have different specializations. And by now, you know that people in math use different vocabulary than electrical engineers. People in physics do use different vocabulary than electrical engineers. And even people, so the lot of electrical engineering faculty come from different backgrounds. My background was always electrical engineering since I was an undergraduate. So the terminology that I'm using comes from that community. There are other faculty who are in electrical engineering, but their first background was either in math or in physics. And they may be more familiar with the others. So having said that, if you hear me say something and it's not that familiar with you, just let me know, ask me, stop me, okay? So now I remember, so the shunt, because I noticed that some people had difficulty with that in the midterm. So what shunt means is like in parallel. So you see here that you have inductors in series and capacitors in parallel. So in shunt configurations. And so from there, we have to do two things. Incorporate the impedance values we would like to see in the filter, and then also incorporate the real frequency we want to see. Because now, in the, need to remember, in the prototype, omega sub c is 1. And the 1 means nothing. It does not have any units, all right? So we have to go through two transformations. One is called the impedance transformation or impedance scaling. And what that does is to transfer all of the resistors into the real value. So every resistor you have, which is usually your source resistor or your source impedance, here in the prototype, all impedances of the source are considered to be real. And as a matter of fact, we always make R sub S to be R sub naught, which is 50 ohms. Remember that. Then we multiply all of the inductors by this R sub naught. Also, G sub naught that you see here is always 1, always 1. All right, that's what I'm telling you, that R sub naught really indicates the value of the source resistor. And for us, we take it 50 ohms. All right, now somebody may tell you that I want you R naught to be something different. In that case, you use a different value for R naught, but in any case, most of the time it's 50 ohms. Then all the inductors are multiplied, okay, as we can say here. And then immediately at that point, I would say, it's not yet totally transformed into an inductor, all right? By multiplying a number, see, I'm trying to help you here. G naught is just a simple number. You multiply a simple number with an impedance, which is R naught, and then becomes an impedance. For resistors, that's fine. That's all we need. But if you go to inductors and you multiply a number with an impedance, then it becomes an impedance. And then we know that we are not done yet because an inductor is not ohms in ohms. An inductor is in henries. So we have one more transformation, and that's going to be the frequency. Now, according to the impedance transformation, we divide all of the C's by R naught. So practically we have this one. When you see dividing all of the C's by R naught, then they become 1 over omega. And again, we know that this is not our real capacitance because capacitances are not 1/ohm. They are farads. And then finally, if your load is in the form of a conductance, you see that? We always divide it by R0. If it is a form of a resistor, we multiply it. In this case, I put the load to be as G sub L. All right, so you always remember that. And then if it's a conductance and you divide it by R0, has the right units. If it's a resistor and you multiply by R0, has the right units. Okay, is everything understood here? Any questions? Let me see.
Where do we get G1,
Yes.
G2, and G3 and G0?
Will I get one? Could you repeat again? I'm sorry.
Sorry. So where does the G0 through G3 values come from? Are those given?
There is a table here. And you will see this table in the book. All right.
Okay.
And
yeah, that totally makes sense.
Yeah. And also be careful which table you read, because the tables are for different. So for element values for maximally flat filter, they're given here. The tables that you will see in another example for equal ripple, or what we call Chebyshev, they're different. All right, they're not the same. And G0 is not included because it's always 1. All right.
Okay.
And also something else. Do you see the last element here, which is 1? Is not part of the order. So you see when n equals 1 and then you have one stage, 1 is not a stage, is like the terminating resistor or conductance, resistance or conductance. So stage 2 has 3 elements because the last one is the terminating load, all right? So remember that. Also, make sure you don't consider that as a stage. Okay, now going down, what I said is that we need to do 2 more transformations, but the next, 1 more transformation. So the next one is the frequency transformation. And now we know that the frequency transformation is only appropriate for the storage elements. How many storage elements we have? L and C. Why do I call them storage elements? Because they store energy, all right? They are called storage elements because they store energy, or others may call them the in reactive elements. You know, either one is fine. Reactive power is imaginary, and in forms of it translates when you integrate it, it translates into energy. All right, so power instantaneous, but when you integrate power over time, you get energy. So only inductances and capacitors have that capability to store energy. Okay, so what you do, only you have to do frequency scaling in those elements, not the resistors, don't touch them. So L, what do you do for all of the inductors? You divide them by frequency. And what do you do for all the capacitors? You also divide them by frequency. All right, so again, while when it comes to impedances, we multiply inductors or the inductive stages, and we divide the capacitive. When it comes to frequency, we divide both. Okay, and now if you do that to the previous 3-stage filter, you get, 2-stage filter, you get with a real value. So your source impedance is 50 ohms. Your load conductance here is 0.02 or 1/ohm. If it's in a resistor, is 50 ohms. And then you have one capacitor, which is 0.5 picofarads, and somehow the farads is missing. And you have one inductor, an inductor here, which is in nanohenries. Okay, now we are gonna do a similar example, and we are gonna do an equal ripple or Chebyshev. Who can tell me what is the difference between a maximally flat and a Chebyshev?
The pass band is, it's more flat with the maximally flat version. And
It's
Chevy Chef
totally
has this
flat.
ripple.
Yes, yes, yes. The equal ripple has a ripple, obviously,
And the Chevy Chef has a steeper drop off after the 3
exactly. And that's why, because somebody will say, well, if I have a flat pass band, of course I like it. That's how I would like it to have. If I could, I would like to have a pulse, all right, for a filter. Everything through when in my pass band and everything rejected outside. Well, that's not possible, at least with what we have, the tools we have available today. So sometimes you ask yourself, what is it more important for me? And then maybe your application is going to tell you that. That is more important for some of you, for some applications, to have a flat pass band, far more important than having a very high rejection. So then you go for the maximally flat filter. But then you may have other applications where it's far more important to have a good rejection because, and I will tell you the applications. Number one, for the flat pass band, let's assume that you have a filter for a system you design, which is developed to receive low signals, all right, low signals, low in magnitude, and or low power, if you like. And then, however, the signal is kind of clean. You don't have other unwanted or spurious frequencies in the vicinity, around the frequency of a band of the signal. In that case, it's far more important to me to not lose any power as I receive the signal. And then if my signal is clean and I worry about frequencies which are far from my pass band, then I would go for a maximally flat filter because I know I'm not going to lose any power when I receive it. Okay, now that's one application. There is another application where you have a signal, but you worry most about the spurious frequencies which are very close to your pass band. In that case, I would rather go with a Chebyshev that has very good rejection, and usually your application will tell you how much rejection you will need to have, and it's going to be a spec therefore for your filter. And I don't care about having these ripples in my pass band because eventually my signal is strong enough and I can manage this through my amplifier and the rest of the system. I don't worry about the ripple. So in that case, you will go for Chebyshev. Now, let us assume that somebody gives you here a filter specs, and they say, first of all, I want a low pass filter. I want the cutoff frequency for the filter to be at 1 gigahertz. And I want my rejection to be 50 dB at 2 gigahertz. In this particular case, I also tell you that I want an equal ripple. And then I want a source impedance to be 50 ohms. Now, let's assume that I do not tell you, and for a moment, I will somehow do that. I'll use a red. And let's assume that I did not have this here. All right, that was not part of the specs. But I will tell you that I want a good quality low pass filter with a cutoff frequency of 1 gigahertz, rejection at 50 dBs, or 50 dBs at 2 gigahertz, which is kind of a good rejection, all right? And then let's assume, again, source impedance of 50 ohms. And now I look at the previous one. You don't know whether it's going to be a low pass or a band pass, but I'm going to the previous table, this one, or in fact, a previous one, this one, okay? And in this one, look at this. It says that if I want to have a 50 dB, so I'm going to draw some new lines here. So when I am at 2 times my cutoff, that means that omega over omega c minus 1 is going to be this line here, okay? And now I'm going to be at 50 dBs, which is this line here. In fact, a little higher. Okay, so how many sections do I need to have? In fact, if the 50 dBs at twice my FC is a very hard requirement, I'd rather go with more sections rather than less. So I will go up here to design it. So practically, I will select n equals 9. 9 sections. I will need 9 stages in this filter. So, however, since nobody has told you whether it has to be equally maximally flat or equal ripple, if I go down to the equal ripple graph, which is right here, and then I look exactly at the same requirements, how many sections do I need to have? 6. Instead of 9, I will have 6. And I would always go for the simplest realization, because as you can see, things can become very complex as you try to implement it. So it tells you also, even when you don't have any specific requirement when it comes to equal ripple or equal, yes, or maximally flat, you go always for the equal ripple, because for the same rejection, you will always have fewer sections. Okay, so that's another way of saying that equal ripple always gives you better rejection. So, and I like fewer sections. So in our particular case, it was given to us already. And so I look and I find out I need 6 sections. So what are my sections? 1, 2, 3, 4, 5. All of the series sections, they are inductors, the shunt are capacitors. Okay. And then I do exactly what I did before, but I'm looking correctly at the correct tables. So they told me, well, I decided that I'm going to go for a 5 dB ripple, because look at the other one is 3 dB. Who wants 3 dB ripple in your power? You know what 3 dB ripple in your power means? At 3 dB down from the top, you lose half of your power. So you'll say, who crazy will put the 3 dB? I don't know. Really, I have never designed a 3 dB ripple filter myself. But I would go for the 0.5 dB ripple. Now, let me ask you this. Did you understand what I said, that 3 dB ripple is 3 dB below the max, and 3 dB means half of the power?
Yeah, that makes sense.
Who has difficulty with this statement? If anybody has a difficulty with this statement, join us for the office hours, and I can be a little more, detailed on what that means, why this statement is correct. Okay. Now, therefore, I saw here that I am at 6 sections. I am here. What is interesting in this particular case is that my 7th section is not a section. My 7th element, which is my load, is not 1 anymore. That's okay. That's not a problem. That means that this filter, to perform at its best, it needs a load different than 50 ohms. That is, all right, what is interesting. Which means, what does that mean in design? That if you have another, in your receiver, after the filter, you have another component, this component needs to present to the filter, not 50 ohms, but whatever impedance the filter needs to see, all right? For the filter to perform well, because if you don't put that impedance, the filter is not gonna perform at its best. Okay, so we now have these numbers for all of the G elements. And now I'm going here and I take all of the elements which are eventually going to lead us into inductors here, and then all of those that will lead us into capacitors there. And then the front element is always 1, and that's your source impedance. The last one is your source, your load impedance, all right? If it's an impedance, you will have to multiply it with your reference impedance, which in our case is going to be 50 ohms. Okay, now, after we find all of these elements here, what is the next? Practically, we have found a prototype. But what is the next? We need to go and apply impedance and frequency transformations. Okay, so you remember, in impedance transformations, all of the resistors and all of the inductors are multiplied by R0, which is the reference impedance, and for us it's going to be 50 ohms, as we all discussed. And all of the capacitors will be divided by R0, all right? Now, frequency transformation. We don't do frequency transformations to resistors, obviously, all right? The resistor does not change with frequency. It remains the same. But we do frequency transformations to both inductors and capacitors. And we divide both of these. And at the end, if we do this and we make the calculations, see what it happens. We find all of our inductors in nanohenries. They come out to be nanohenries if you put all of the units there. And the capacitors in picofarads. And that is a filter that is low pass. So now I'm gonna, after this, after my statement, I will ask you a question. So this is a low pass filter. It has a cutoff frequency of 1 gigahertz. It has a 50 dB rejection at 2 gigahertz and has an equal ripple in the pass band, which is 0.5 dBs. And reference impedance, so the source has an impedance, which is 50 ohms. Okay, any questions so far? All right, I have a question for you. But I would like to ask the question in the simplest filter which we solved, which was the maximally flat. You remember? The filter we solved, where is it? Here. That's a maximally flat filter. So this one is a low pass. Let me write here to remember. Low pass. What did I say about FC? 10 gigahertz. It needed to have, how much rejection did I say? Let me see. Don't remember the rejection. How much it was. It was part of this. It was 20 dBs at 3 times. So the rejection was kind of, that's why you have so few sections, because it was low rejection. So rejection, 20 dBs at 30 gigahertz, 3 times the cutoff, right? and the source impedance was 50 ohms. So this is your filter. Now, if you were to take my word the way it comes, you will say that I am contradicting myself, because I have told you previously that if you have an LC configuration, what kind of a filter is it? What did I tell you in the past?
Used to call it a bandpass in the past.
What is resonant, exactly. What it resonates, all right? It's like a simple LC resonator. What do you think? Is that true? Why is this LC resonator gives me a low pass filter? What happened, you think, or you suspect? Was I not right when I said it's an LC, every LC has a resonance?
I assume it's because the inductor is much more prominent than the capacitor in this case.
So kind of, I think you are on the right path, but I will tell you what I would say. This is not very different from some of the LCs you saw and you were confused a little bit because the inductor allowed the DC to go through. And you remember what we said at the time, that yeah, you may have circuits that allow the DC to go through, but they may still be resonating. You remember that statement? So if you remember that statement, we said, I will come back to it to remind it to you and say, yeah, look at this example. We do have the DC come through. Because of that, it allows us to create a low pass filter. But now I will prove to you that it still has a resonant frequency. All right. But what happens to this resonant frequency? The resonant frequency is extremely high. So it's so far away from my operating frequency that I don't care anymore. And let's try to find it out. What is the resonance of this LC? Forget about the load and the source for a moment. So let's look at, we want to look at the unloaded, all right, resonance. Let's look at this alone. Do you remember how much is how we find the resonant frequency?
Is it 1 over LC?
Yes. So let me call that intrinsic. Okay, this is an intrinsic resonant frequency. And it's going to be, and I will call it, let's see, R, just to differentiate from anything else. It's 1 over square root of LC. Let's see how much this is. This is 1 over, how much is L? Square root, let me put here, 0.336, 10 to minus 9. How much is capacitance? Times 0.5, and then watt times 2 minus nano, and then what is pico? All right. How much is this? This is going to be 1 over square root, let's say approximately is going to be 0.15. And then it's going to be 1 over 10 to what? I mean, this is times 10. And then minus 11. Do you agree with this? It's going to be therefore 1 over square root of 1.5. And this 10 to the 11th. Any comments about that? Am I right? Let me see. Now, if I use my calculator, it's going to be
7.7 to the power of 10.
Okay, so it's 7.7, 10 to the 10.
And then I'm getting 12.28 gigahertz.
Okay. There is a difference between the two. Let me do this also. And then inverse. Why do I find different from both of you?
I got 74 gigahertz.
Well, this is radian, radians per second, but
Ah, okay, that's why. Okay, got it. Yes, all right, of course. So this is in radians. Okay, so you're talking about, yeah. So F sub R, but I still find slightly different, maybe because I round it up, my guess is, okay? I round it up to 0.15. Yes, and then times 10 is 1. So anyway, let's with my round off error, that is going to be let me see, 81.64 that I get. And then this is going to be, it's going to be 12.9 gigahertz. Am I right?
Yes.
Okay. So practically that looks like this. Let me see. Okay. So how is this gonna look if I add one more page here? No, I don't do it like this. Where am I? There. Add a page. Then this is gonna, what happens at resonance? Let's also see what happens at resonance. How much we have an LC like this before we say how it's gonna look. We have an LC like this. Okay. So what is gonna happen at resonance? From this, your load is here. Let's try to do it just thinking physics right now. The load is here, and yes.
I believe the FR is not correct because it's 80. The radian per second is 81.6 times 10 to the 10th.
Yes.
So
Oh, 10 to the 9th, excuse me, I should. Yeah, 10 to the 10th.
Then it should be 129 gigahertz.
Let me see, 1 second.
well, you divide by 2 pi.
Yeah, then it's still.
It should be higher. Yes, you're right. Let me check it once more. He's right. I mean, Zehin is right. Let me see. To take it once more. Square root.
I think it should be 8.16, not 81.
Ah, see, okay. Maybe I have already, but it's 10 to the 11th, all right? So it's 10 to the 11th, 1.5 square root inverse, and then that's times 9, 81.6, that's where I made the mistake. That's to the 9th, you agree? Look at that carefully. All right, now, okay, I forgot to do this, and then that makes it correct. Okay. All right. Now still 13 gigahertz from like 1. Was it 1 at this one? No, it was 10. Okay, 13 is not very far away, but it's 13. So, and I wanted to have 20 dB. So here is what's going to happen with this one. Let's see what happens at resonance here. What happens at resonance with this circuit? You have a source. Let's continue with our analysis. You have a source here, and this source connects, well, let's do it ideally now, connects to this circuit. What happens at resonance? At resonance, anything that, so you charge the capacitor, all right? So the capacitor is charged, and then what happens? It's all discharged through the inductor. If that were to be like this, practically, you will have an ideal resonator, and all that when you charge the capacitor, it goes through the inductor, from the inductor to the capacitor and so forth. Here you have a load, and your load is 50 ohms. So what happens is that you charge your capacitor, it releases energy into the inductor and goes through the load. And if the load is a 50 ohm load, then practically it's going to dissipate. And then so what happens when you plot the performance, while it is in a low pass filter, because it allows the DC to go through, and then it will go like this. At some point, because it's a loaded resonator, it has a 50 ohm resistor, then practically your resonance is going to be buried. Because why is that? Because, or it may be a small glitch here, depending of course on how much you loaded the resistor. And why it's happening there, why is it so low there, is because the current that you are sending through your inductor here, it goes and is dissipating in the resistor. Now, if your load was not exactly a resistor in this filter, but your load had, let me also do the following. If your load, it was a complex load. So you had some kind of a resistor, but also an inductor, say it was a reactive load, all right? So you would have something like that and like this. Then what happens in this case? In this case, less is lost in the resistor, and more than this inductor, which is the load inductor, with this capacitor and then the other inductor of the filter will create a stronger resonance. So if you were to put this filter into this load, then you could have seen something like this. All right. So why therefore is important to recognize the resonances of a filter, and why I was so very specific about that? Because if you don't recognize the resonances, you will never be able to understand if you see that you have a problem with your initial filter. You will not be able to understand why you have something like this. Okay? Do you have any questions like this? The other thing I want to tell you before we go there, a lot of times you will hear people talking about, and we will come back to it later, talking about an unloaded Q for resonators and a loaded Q. Unloaded Q is what I call the intrinsic resonance. Means I don't look at the load, because depending on the load, I look at the intrinsic resonance of my circuit. When there is a load, if the load is very resistive, then it dumps your resonance totally. All right? You know, you have heard about that in RLC circuits, in circuit classes. Is that true? You have heard about damped resonances?
Yes.
Okay, that's what happens here. If your load is resistive, then it dumps the resonance and your loaded Q becomes very low. A strong resonance gives very high Q, all right? A damped resonance, because you have a resistive load and absorbs all the energy, dissipates, all of the energy that goes between L and C is dissipated by the resistor, then your Q can be very low. So why is that important to remember? Because as a filter, you may have a good Q, but then when you load it with something that is not being part of your design, then the Q of your filter can go very low. And that's why you need to pay attention to what loading your designs are telling you have to have, and what you load you provide yourselves. We will see that more when we go to bandpass filters. But I wanted to come here because I wanted to remind you that some of the things that we were discussing in the LC or RLC resonators. So always then keep in mind the following, that if you have an LC, you will always have an intrinsic resonance, all right? It does not happen if it's only an L or if it's only a C. Why it is important to recognize the intrinsic resonances of your circuit? Because whether they are going to be problematic, like here in the filter or not, depends on what kind of load you're going to use. A resistive load is going to make it very low, but a load that is reactive can make it very high here. So try to anticipate that and try also to look for this if you have something that bothers you in your design of your filter. Okay, any questions so far?
I have a quick one. With that drawing that you have there with the resonance that is pretty significant, would that still be considered a low pass filter? Because
but it's a bad low pass filter.
Yeah, it's a bad one, but it's still right?
It's a low pass, yeah, for
Okay.
this design, yes.
So what would take this graph and make it a band pass, like how you defined it before?
Yeah, now we're gonna go to the next topic.
Okay.
All right. So now, unless you have any other questions, what time is it? Okay, we're ready to go to the next, and I'm gonna tell you very briefly, and I will start with the next next time.
So
yes.
just real quick question. So at
Yes.
For a parallel LC at resonance, impedance or input impedance is maximized and power is minimized, right?
Oh, you're talking about, it depends on the configuration. You're talking about this one.
Right.
The middle one. Yes. What happens is at resonance, practically, that works like an open circuit. Because you charge it, I mean, if there is a true LC without any resistance, and that's not true, all right? There's always some kind of resistance. But at resonance, it allows everything to go through. This one you're talking about. Okay?
Right.
Yeah. At resonance, after you have charged the capacitor, then practically becomes like it's like almost getting disconnected from the main circuit. See here, it's like that does not exist anymore because the capacitor discharging the resistor and the resistor charges the capacitor again. And then there is a loop there.
Okay, I see. So so in series resonance, the impedances are equal though.
In a series resonance, where it's like this,
or like the impedances cancel out.
So the pins can, yeah, in series resonance like this, at that moment the impedance cancels out. But if you have something like this, then it becomes like an open.
Okay, I see.
All right. So, okay, the last thing, and then I will just talk about this, and then we'll see here. Look at this. This is in fact self-explanatory. It tells you now how to go from a low pass to a high pass, a band pass, a band stop. So your L in the low pass, you just replace your L with a capacitor, your C with an inductor, but of course with the appropriate values. You have to change the values as well. In band pass, every inductor becomes a series LC, every capacitor becomes a shunt LC, but with the appropriate values, where delta is the percentage bandwidth. and omega is considered to be the center frequency of the band. And a band stop is treated similarly. It's just the bandwidth is going to band stop, all right, in the band that stops. And then it's given by this. So practically, it's just another transformation. And it's a very simplistic one. You just have to use this table then to go from a low pass after you develop the low pass. You have to develop your low pass filter and then you transfer it, all right, accordingly. Is that clear? That's what we do here. Now, in this particular case, obviously, you have not done the impedance transformation yet. That's why you also do a transformation, an additional, at least for the high pass, to change. But we'll talk about this in detail. But we're going to use this table to see how we're going to go from one to another. All right? For next time. Any questions? Okay, so in half an hour, we are having our office hours. So I will invite you to come. We can talk more about this. We can talk about your homework. The homework is rather simple. I just gave it to you so you can just practice a little bit with this. But we can talk about that as well. Okay, so I will see you later in half an hour.